G'day, let's continue our look into our chemical bonding unit. Today we are looking at intermolecular forces, the concept of electronegativity and bond properties, where our lesson objective is to understand the different intermolecular forces and their implications for a molecule's physical properties, and then to explain these forces in terms of electronegativity and polarity. As always, the outcomes we'll be addressing from the Cambridge curriculum. So prior to this, we've looked at our types of chemical bonding. We've looked at our ionic, our covalent, and our metallic. We're going to look now at molecules and how molecules interact with one another. So two bits of terminology just to introduce right off the bat. Inter versus intramolecular forces. So far we've been looking at intramolecular forces. So these are our covalent bonds. These are our forces within the molecule. Now what we're going to look at is intermolecular forces, and these are forces between the molecules. So these prefixes intra and inter, you can think in terms of an intranet versus an internet. The intranet is all locally, it's all within a certain thing, whereas the internet is externally, it's beyond it. Same thing with intra versus inter. So we've got these really strong intramolecular forces, these covalent bonds, the forces within the molecule. However, the forces between the molecules, the intermolecular forces, are much weaker. And there's three kinds that we're going to be looking at. Van der Waals forces, permanent dipole-dipole forces, and hydrogen bonding. We're obviously going to go into these in a lot of detail. But to begin with, we're going to introduce this idea of polarity. Polarity comes from poles. You think of the word poles in your everyday life. It means sort of two ends. You got the North Pole, you got the South Pole. You got poles on a magnet. You got a positive end, you got a negative end. Same thing within molecules. You got poles on molecules, polarity within molecules. The electrons in covalent bonds are not necessarily evenly shared, and this is what's called electronegativity. So we looked at covalent bonds as this idea of two atoms sharing a pair of electrons to create a strong intramolecular force, i.e. a covalent bond. However, we know that not all atoms are different. Not all atoms are the same. They're different. They've got different amounts of electrons. They've got different amounts of protons. They're different sizes. They've got different radius, etc., etc. So what that means is that if we got two atoms sharing an electron pair, they're not necessarily going to share it. It's not going to be an even distribution necessarily of that electron pair. And this is this concept of electronegativity. Let's look at it. We create a pole of charge on each end of the molecule. So if we've got something that is holding the electron pair a lot closer to it, then it's going to have a slightly more negative charge because that electron pair is being held a little bit closer to it. We're going to look at some examples to explain that more in just a moment. Fluorine is our most electronegative atom. So let's think about this. If we got something like HF, hydrofluoric acid. Now we've looked at this idea of the covalent bond. This is the intramolecular force, is them sharing a pair of electrons. Like that, that's our covalent bond there. However, fluorine is a much more electronegative atom. So what this means is that this isn't a symmetric distribution of charge because of the chemical properties of fluorine, because of the amount of protons it has, because of the number of shells it has. This electron pair is actually being distributed a lot more closer to the fluorine atom than it is to the hydrogen atom. So I mean, if I draw this in an exaggerated sort of fashion, we might have something like, how exaggerated does that make? A bit more exaggerated. Where this bonded pair is still being held by this hydrogen, but it's being held a lot closer by this fluorine atom. So what that gives it gives it a partial negative charge because this fluorine atom has that little bit more negative from that electron pair than the hydrogen does. So you can think of this as if, you know, a tug of war between a strong person and a weaker person. The stronger person's pulling that electron pair closer to it, and if the electrons are negative and the electron pair is slightly closer to that atom, it gives it a partial charge. So if electronegativity is equal between atoms, the bond is nonpolar. There are two situations where this can arise. If I have a covalent bond between two atoms that are exactly the same, such as bromine gas, we have Br bonded with Br like So, one covalent bond. These two atoms are chemically identical. So this electron pair, because these two are the exact same atom, is perfectly distributed between these two atoms. So there's no slight charge. They're equal in electronegativity. Whereas when they aren't the same atom, as was in the case with hydrofluoric acid, let's think of something like, I don't know, let's use hydrochloric acid this time. These two atoms are not chemically identical. This one is more electronegative, so it's going to hold the electron pair slightly more tightly to that one, so it's an asymmetric bond. So we have a symmetric, is that how you spell symmetric? Two M's? Yeah, we'll stick with it. And an asymmetric over here. So this is non-polar, this is a polar. So this is going to have a positive and negative pole, positive and negative charge, whereas this one isn't a polar, it's a non-polar bond. So if electronegativity is equal between atoms, the bond is non-polar. This would happen when the atoms are identical, diatomic molecules, Br2, F2, Cl2, those kinds of things. And also when the electronegativity of the two atoms are very, very similar. And the most common case of this is in a CH bond. So in the case of a CH bond, the electronegativity values, so how much the atom will want to hold that shared electron pair, is basically the same for carbon and hydrogen. So this would also have a symmetric distribution of the shared pair electrons. So this would also be a non-polar bond. So CH is a non-polar bond because the electronegative values are so similar. Diatomic molecules, when a covalent bond is shared between the same atom, would also be a non-polar bond. This all begs the question of how do we know which atom is going to be the more electronegative atom? And there's trends in the periodic table that we can look at in order to determine this. So let's have a definition for electronegativity after discussing it. The ability of a particular covalently bonded atom to attract the bonded pair of electrons to itself. Now, fluorine is the king of or the queen of the electronegativity. That's the boss. That is the most electronegative atom on the periodic table. And that's just all due to its nucleus charge to the number of shells, that ratio with itself. So even though other atoms might have a higher nuclear charge, and you might think that would want to attract the electrons more to itself, which would be correct. However, we've got to think of the quantum levels. They've got more quantum levels, so that outer pair that's being shared is further away. So fluorine is the most electronegative because it just has that perfect ratio of quantum shells to nuclear charge. So as we go towards fluorine that way, we increase electronegativity, and as we go towards fluorine this way, we increase electronegativity. And you can see that pretty easy to interpret with color-coded here. The more red it is, the more electronegative. So if we have something like a bond between a carbon and a nitrogen, we know that the nitrogen would be the more electronegative one because it's closer to fluorine. If we have a bond between a hydrogen and a bromine, bromine would be the more electronegative one because it's closer to fluorine. So these are the general trends like so. Polar bonds. When electronegativity between covalent bonds of an atom is different, the more electronegative atom attracts the pair of electrons in the bond closer towards it. The electron distribution is asymmetric, so the two atoms will have partial charges and the bond will be polar. So it's a little bit different to full charges when we talk about donating or accepting electrons. When we're talking about ionic bonds, they get a full negative or a full positive charge. However, this isn't the same as that because there's still a covalent bond. So even though one atom's attracting the electron pair more, it still belongs slightly to the one that's attracting it less. So we don't have these full charges, we have these partial charges. And how we designate these are calling them delta positive with this delta plus. This is the Greek symbol for delta. And delta negatives. So they're not as strong as full positive and negative charges like we see in ionic bonding. They're just these partial delta positive and delta negatives. The higher the difference in electronegativity, the more polar the bond is. So we can see we've got these values for electronegativity, 3.98 for fluorine, 2.58 for sulfur. The bigger the discrepancy, the bigger the difference between these, the stronger that polarity will be, the bigger the charge. The degree of polarity is measured as a dipole moment, and we show the direction of the dipole with the following arrow that looks like this, where the arrow points to the more negative end. So the arrow is pointing to the more negative end, and it's got this little symbol there. Let's look at some examples. Show the polar bonds on a HCl and NH3 molecule using delta charges and dipole arrows. Rightio. Let us go to the whiteboard and draw some molecules. So first thing we have HCl, we did that before, so that'll be a good one to start with. We have HCl. If I look at my periodic table, my chlorine is closer to the fluorine than the hydrogen is, so our chlorine is more electronegative, so this has the delta negative charge. Consequently, this will have the delta positive charge. This is saying this electron pair is slightly closer to this chlorine atom. That means it's going to have a partial negative charge, which I denote with my delta negative. That leaves this one with a partial positive charge. And then we can show this direction using our arrow, where the arrow points to the more negative end. What about NH3? Well, we've got to consider our molecular geometries. If you want a revision of that, we got a video a few videos ago where you can look at that. Nitrogen has this trigonal pyramidal shape. Now in this case, we've got one nitrogen bonded to 3 hydrogens. So nitrogen is a more electronegative atom than hydrogen, and we know that, just to reiterate, based on the periodic table, nitrogen is closer to fluorine than hydrogen is. Nitrogen is 3.04, hydrogen is 2.2. You don't need to remember any of these values, just the trends in the periodic table. So if I were to denote one as delta negative as one as delta positive, it means that the nitrogen is delta negative. All 3 of these hydrogens will be delta positive because all 3 of these hydrogens are having the shared electron pair pushed slightly away from it, which means it's going to have a slightly more positive charge. You can show it the dipole moment with the arrow. Remember, the arrow points to the negative end, so I would have 1 there, I would have 1 there, and I would have 1 there. So they're our polar bonds. Let's keep exploring because we can have polar bonds, but we can also have polar molecules. A polar molecule forms when the spatial arrangement of chemical bonds leads to a more positive charge on one side of the molecule than the other. It requires polar bonds, however, we can have a molecule with polar bonds being a non-polar molecule. So what we need for a polar molecule is a net polar charge in one direction. And what that net polar charge is the average, the nets of all the dipole moments in the molecule. So for HCl, this is very, very easy. This is going to be a polar molecule because we've got one polar bond and we've got a very clear negative and positive end. So this will be a polar molecule because we have a pole on that side, we have a pole on that side. This one here, we have 3 dipole moments. If we were to get the net, we would have a net dipole moment going like that. So this has a very clear negative end and a very clear positive end. So this would also be a polar molecule. If we have a non-polar bond, if we have our Br2, this is a non-polar bond because both of these atoms are exactly chemically identical, so they're going to symmetrically distribute the electron pair between them because they're both going to attract that electron pair the same amount. This is a non-polar bond, so this is going to be a non-polar molecule. It has no poles. Let me go back to my slides to see what I got next. Let's consider CHCl3 versus CCl4. So I'm going to draw both of these. These both have carbon as a central atom. Carbon with our sp3 hybridization, we get a tetrahedral shape. So we've got one which is CHCl3 and one which is CCl4. 1, 2, 3, 4. Let's start over here. In this case, chlorine is the more electronegative atom than carbon. You can find that out by looking it up on the periodic table. So this is going to be closer to fluorine. So these are all delta negative, delta negative. This is a delta positive. CH is a non-polar bond, so we don't have any pole there. Over here, we've got 4 chlorines. So we've got 4 delta negatives, like so, like so. So we can do the dipole moments with the arrows where we're pointing to the more negative end of the bond, like so. Whereas this one is going to look like that. Now, this is where we get the difference between a polar molecule and a non-polar molecule, even though we've got polar bonds within the molecule. Within this one, if we were to get the net sort of dipole moment, it would be like that, because all these three arrows would sort of even out, and we've got a very clear negative end, we've got a very clear positive end, so we would have a polar molecule. It's a molecule that has a pole. It's got a positive pole, it's got a negative pole. However, over this side, all of these net dipoles would cancel out. So we don't have any clear positive end. We would have a non-polar molecule here because we've just got negative all around it. There's no positive end, it's just negative end on this side, negative end on that side, negative end on that side, negative end on that side. So there's no poles to it. In order to have a polar molecule, you need a positive pole and a negative pole. Whereas this one has no positive pole, it's a non-polar molecule, even though it has polar bonds. The electrostatic charge from polar bonds will also determine its reactivity. We're going to look at that in just a second, not right now. This is why molecular geometries are important. This is why we have to learn all our trigonal planar and our linear and our nonlinear and our tetrahedral and our pyramidal, etc., because it's going to affect if we've got a polar molecule or a non-polar molecule, because the geometries are all dictating which end's going to be positive, which end's going to be negative. Questions. For the following molecules, determine the shape, bond angles, any dipoles, and the overall polarity. So we're linking a whole bunch of things together. Pause now if you want to have a go. I might show you what they are first so you can actually do it. Pause now if you want to have a go, and then check when we do it right now. Rightio. So the first one we're given is H2O. Oxygen has two non-bonding electron pairs, two bonding electron pairs like so we know it's non-linear. In a non-linear, we know the bond angle is going to be 104.5 degrees. That is a number that you do have to learn. The shape, it is a non-linear molecule, also called V-shaped. It goes by a few names. We're going to call it non-linear. Any dipoles? Oxygen is more electronegative than hydrogen because it is closer to fluorine than it is hydrogen. Is closer to, it's the closer one to fluorine is what I'm trying to say on the periodic table, so it'll be delta negative. The overall polarity, we're going to have an overall polarity in that sort of direction. So that means we are going to have a nonlinear polar molecule. Did I answer everything? Bond angle, shape, dipoles, and overall polarity. All right, CF4. CF4 is going to look like this. Carbon is going to make tetrahedral because it is sp3 hybridization. Fluorine is the boss of electronegativity. So these are all going to be delta negative, delta negative, delta negative. We can do the dipole moments like so. We can name it. It's a tetrahedral. The bond angles in tetrahedral is 109.5 degrees. Again, that's a number you're going to have to learn. This is going to have no overall polarity because all of these four dipole moments are going to cancel each other out. It's going to have no net dipole, so it's going to be a non-polar molecule. Let us keep going. CO2 was the next one. I'm going to squeeze CO2 in here. And we're going to have space. Yep. CO2 is going to be a linear molecule because the carbon has no lone pairs of electrons. If it's linear, it's going to be a straight line, 180 degrees. Now, oxygen is more electronegative than the carbon is. So, I keep forgetting to do my delta positives in here. I need to remember the delta positives. So we're going to have two polar bonds, like so. However, we're going to have no overall polarity because the net polarity is going to cancel each other out. So this will be a non-polar molecule. It's got negative charge all around it. There's no positive end, it's just negative ends. Non-polar molecule. And our very last one, which I'm going to squeeze down the bottom here, over here, Br2, Br, linear molecule, 180 degrees for the bond angle. These are the same atom, So this is going to be a non-polar bond, so we can't show any dipole moments because there aren't any. It's a non-polar bond, so it's going to be a non-polar molecule. Non-polar molecule. There's no poles on it because there's no polar bonds, so there's no charge. Excellent. Let's look at the last few things relating to this part of the lesson. Reactivity and bond length, bond energy, and polarity. So the bond polarity we've looked at a lot. Just to recap, it is the separation of electric charge along a bond due to asymmetric distribution of a bonded electron pair. In general, the more polar the molecule, the more reactive. And this is because electrostatic attraction from polar bonds leave molecules more susceptible to attack from oppositely charged species. For example, a hydroxide reacting with ethane versus chloroethane. So if I erase all these very quickly and draw an ethane molecule versus a chloroethane molecule, ethane, these are all going to be hydrogens. Chloroethane, we're going to have one of these as a chlorine. So our CH bond is a non-polar bond because the carbon and hydrogen have very, very similar electronegative values. So they're going to share that electron pair pretty even. So there's no polar bonds. However, over here we do have a delta negative and we do have a delta positive. So a lot of chemical reactions occur from electrostatic attractions between charged species. So if I've got an OH minus, like so, we know that positive and negative attract each other. We know that that's due to the electrostatic force of attraction. So if this is a negative charge and this is a slightly positive charge, there can be a chemical reaction that occurs here, whereas this is a negative charge, but this has no charge. So this one's not going to be electrostatically attracted at all to this. So the more polar a molecule is, the more reactive it's going to be because this electrostatic attraction can cause chemical reactions to occur. So that's our bond polarity. We have this other term called bond length. We have two bonded atoms in a molecule. In general, single bonds are larger than double bonds and they are larger than triple bonds due to the greater attractive force between electrons and nuclei pulling them closer together. Therefore, the shorter the bond, the greater the bond energy. So let's think about this. If a single bond is larger than a double bond, it means that the electron pair are further away from those respective nuclei. They're further away from those respective nuclei at each end of the bond. They're going to be held less tightly because the attraction between the negative electrons and the positive protons is related to the distance. So if we've got a single bond, double bond, and a triple bond, it means that shorter bonds are going to need more energy to break them apart. So we could say that a double bond in general is stronger than a single bond, triple bonds are stronger than double bonds. So let's look at this bond energy in just a bit more detail. Bond energy is the energy needed to break 1 mole of a particular bond in 1 mole of gaseous molecules. Molecules need to collide with enough energy in order to break the bonds that are present. So in general, it's a combination of all of these factors that will determine the reactivity of a molecule. Excellent. That concludes the first part of the lesson. Now for the second part, we're going to go into the types of intermolecular forces that can exist in molecules. Everything we've been looking at is all intramolecular forces. So the electronegativity and the bond polarity are all existing within the molecule. Now we're going to look at how the molecules interact between themselves based on these phenomena, based on if they got charges and so on and so forth. So we've got 3 types of intermolecular forces that we need to be familiar with. The first is called dipole-dipole forces. Dipole-dipole interactions result when 2 dipolar molecules interact with each other through space. When this occurs, the partially negative portion of one of the polar molecules is attracted to the partially positive portion of the second polar molecule. So quite simply, just electrostatic attraction of our polar molecules. So let's look at an example in the case of 2 hydrochloric acid molecules. So I got a HCl and a HCl along with, however many other HCls are existing in my, let's say, a little beaker of it. So chlorine is going to be partially negative, hydrogen partially positive, partially positive, partially negative. Quite simply, dipole-dipole forces is just the electrostatic attraction between the delta negative and the delta positive. No different to any other kind of electrostatic attraction that we've looked at in ionic bonding, in our atomic structure. It's all just electrostatic attraction between a negative and a positive. So it's a partial negative and a partial positive, so it's not as strong as in an ionic bond, but we still have a dipole interaction. Our second type is hydrogen bonding. Now, hydrogen bonding is just a specific type of dipole-dipole interaction that's a bit stronger. So it occurs between the electrostatic force of attraction between a hydrogen atom, which is covalently bonded to a more electronegative atom or group, particularly the second row elements nitrogen, oxygen, or fluorine. So this is the strongest type of intermolecular force. So when you have a hydrogen bonded to a nitrogen, oxygen, or fluorine, our nitrogen, oxygen, and fluorine have such a high degree of electronegativity, if you look at those values on the periodic table, and our hydrogen has such a low degree that when these are bonded together, we just get a particularly large pole in the molecule, which makes a particularly strong dipole-dipole interaction that we call a hydrogen bond. So to look at an example of that, if we got hydrogen bond. So I got two water molecules. So I got OH2, like that. I'm gonna have a delta negative, delta positive, delta positive. And then we'll have a second one, like so, delta positive, delta positive, delta negative. It's just the electrostatic attraction between the delta positive and the delta negative. However, because it's a hydrogen that's bonded to an oxygen, or in the case of NH3, that I'll do down the bottom here, it just makes a particularly strong dipole-dipole interaction that we call a hydrogen bond. So when it's with an oxygen, a nitrogen, or a fluorine. So another example like this, we could show the delta negative there, the delta positive there. We would just have a strong hydrogen bond between those two molecules. So these are both just electrostatic attraction between the slight positive and the slight negative, where hydrogen bonding is just a sort of extreme example of dipole-dipole forces. Nothing too out there or new that we haven't seen before there. Van der Waals forces, on the other hand, are quite different. They're a bit more in depth, and you might see them go by the name London dispersion forces as well. They're describing the same thing. Van der Waals forces is the weak force of attraction between molecules caused by the formation of temporary dipoles. So this dipole-dipole is a permanent force. So these are permanent dipole-dipole interactions when we have a permanent charge due to the difference in electronegativity. However, you can also get temporary dipoles that form just due to the nature of the atom. So the weak force of attraction between molecules caused by the formation of temporary dipoles, caused by correlations in the fluctuating polarizations of nearby particles. It occurs in all atoms and is the main attractive force in non-polar molecules. So we've talked before about, if we go back to our atomic structure, and in particular about how the electron exists, we said that the electron's existing in an orbital, which is a region of probable electron density. So because the electron is sort of constantly moving and fluctuating and changing, if you need to recap on that, we've got a video a few back that you can look at. What can occur is that just sort of by chance, one side of the atom, and in this case the molecule, can have more negative charge on it at that moment than the other side. So if I draw a picture to sort of illustrate this, if I've got a sort of nucleus, I got some sort of molecule with an electron cloud around it, because of the fluctuating polarizations, it could just occur that at a given instance, you have more negative charge on this side than we do on that side, because our electron is in constant flux, it's constantly changing. So it just happens that in a given moment, we get more negative on one side, we get a temporary dipole forming, not a permanent, because in the next moment, that could be back to being an even distribution. Next moment after that, it can be another distribution of charge. However, when we do get more charge occurring on one side, and if we have another atom, so I've got two nuclei with an electron cloud around it, If this all of a sudden has a temporary dipole, well, this now has a negative charge that's going to repel the negative charge over to this side like that and create a more negative charge on that side because of the fluctuating polarization that's occurred in this instance. This can then cause that in another one, cause that in another one, so on and so forth. So we get all these temporary dipoles, these weak van der Waals forces that just happen to cause a interaction and cause a small force of attraction between molecules. So the more electrons that we have, the greater the van der Waals forces we will have, because the electrons cause a temporary dipole. If you've got more of them, you're going to have a stronger van der Waals forces. Now, these van der Waals are essentially existing in all atoms, so sort of every species will have them. However, they're the only force that's occurring in our non-polar molecules. So if we had this as a Br2, for example, our Br2 gas can have intermolecular forces due to this van der Waals forces because a temporary dipole will be introduced on it just due to the random fluctuating nature of the electron cloud and the electron density. So depending on if we have dipole forces, hydrogen bonding, or van der Waals, these will all affect the physical properties of different molecules based on the strength of those attractions, but that's something that we're going to be looking at in our next video. So with that, we conclude today's lesson. What have we looked at? We've described hydrogen bonding using ammonia and water as simple examples of molecules containing NH and OH groups. We've understood in simple terms the concept of electronegativity and apply it to explain the properties of molecules such as bond polarity, the dipole moments of molecules, and the behavior of oxides with water. This oxides with water we're going to look at a bit further down in the course. So we haven't really covered that, but we've covered everything else there. Explain in terms of bond energy, bond length, and bond polarity, and use them to compare the reactivities of covalent bonds. And finally, describe intermolecular forces, van der Waals forces based on permanent and induced dipoles, as in, for example, CH3, Br2, and the group 18 elements. As always, tasks, if you want to pause and consolidate your understandings, they are there available for you, one column at a time, working from the bottom up. Thanks for your time. I will see you on the next one.